Hi. Aha. Hi. All right. Hi, Maisha, if I may. Say hello, Elizabeth. Excellent to see you. Hi, May. I mean, thank you. Um, and and hi, Jayla, and hi, Lizzie. And yeah, I was actually, oh, there he is. Oh, whoa, weird. Okay, well, there's John. That answers that question. And I'm not sure which audio thing, but there we go. Okay. Hello, Noel. And whoa, it's getting, all right. It's already getting hot in here. Okay, I'm going to get going here before it gets ugly. It's good to see everybody. And hello, Stephanie, also. And hello, said Manuel. I think that's okay. Oh, I'm sorry to hear that. I mean, thank you. Me too. I mean, whoa, there's not, wow. Okay. Hey, Stephanie. Okay. No, I'm going to get rolling. Here's the deal. I'm going to get moving fast today. Um, we're still in the middle of homework one. As I warned, caution, homework one takes a while. There's a lot, right? There's a lot, like homework one is actually sort of like the template for a lot of different subtopics that we need for the rest of the semester. So we always do every semester spend a bunch of time on homework one and laying down all these things. So again, just so you know, we're going to be on homework one for a while. We're not going to assign anything new for a little while. I have some game turns that I have to get back to you. You have a game turn to get into me tonight. But and I still have to get back homework one to most of you, but we're going to be on homework one for a while, including certainly today. And let me also say that beginning this Friday, when you do have lab, I want to reiterate that as of this Friday, you do have lab back in the building, in person, in room 3.65, the physics lab that perhaps some of you have never been in before, perhaps all of you have never been in before. That will be with Professor Walters this Friday in person. Please be there. I'm very excited that you'll all be together. I'm going to also say right now, I'm going to pick up from where we were last. Yeah, I'm excited about that. That is awesome. I'm going to pick up from where we were in the material last Wednesday. Sweet, me too for you. I'm going to pick up the material from where we were last Wednesday, but a couple of sort of important logistical aspects of that. Number one, as of last Wednesday, what we this is all, in the context of homework one. This is all in the context of question 4, which I'm spending a while on now. Question 4 shifts us all of a sudden to a consideration of energy and work methods rather than acceleration and force methods. Like question 4 on homework 1, if you recall, it says in the middle of the page here, is at x equals 0, what is the instantaneous speed? And what we said last week was because force and therefore acceleration are varying continuously as a function of position, we can no longer use constant acceleration equations. We can no longer use kinematic considerations. We now we have to develop other methods or ways of solving this problem. The way that we solve this type of problem, is we introduce a concept called work, and we literally introduce it. That is, we define work to be the integral of force with respect to position or change in position, i.e. displacement. So we're literally introducing a new sort of mathematical construct that is the continuous sum of all of the products of force times little displacements. We're doing that on purpose because the force is changing throughout every displacement. So we're about to get into work and energy. Now, here's the thing. That's about as like what's on this page right here is about as far as we got last time. And all of a sudden it's bringing calculus into our class, and not just calculus, but integral calculus. I want to make clear to you 2 things. One in the class this morning in the other section, I got very involved in this. I spent like the entire 75 minutes actually trying to unpack why we're introducing an integral, what an integral means, ultimately how to solve an integral. Like in short, I try to teach the calculus, okay, in a physics kind of way. I'm not, even though calculus is a prerequisite for this class, from my experience, just because you did it a lot doesn't mean you like doing it. Just because you got through a lot of calculus doesn't, for many of us, just means we just got through it. Certainly that was true of me at this stage. Many of us entering this class are still a little bit uncomfortable with integrals, particularly like many of us, certainly me, when I was in this stage, I could do integrals in a math class when I was asked to, if they set them up for me and told me do this integral, or especially if they said do this method, like trigonometric integral or u substitution or something, I could do it. But I knew in my heart that if they ever said to me, do you think an integral would apply here? Do you think this situation would require an integral? And if so, can you set up the integral? Can you decide whether this needs an integral or not? And can you set it up and then decide what method to use to solve this integral? Do this now. I knew in my heart I'd be toast if that ever happened in a math class. And when I got to physics and thought that was about to start happening, I was absolutely panicked. And indeed, in physics, we are not about practicing how to do integrals. We're about, oh, sometimes we need to do integrals and we need to know when that is. Sometimes we have to introduce them and then we have to know how to set them up and then we have to solve them. Okay, that can be intimidating. And I mean, if you're not intimidated, that's great. But that could be intimidating even if you've had 7 years of calculus coming in. What I'm here to say is, let's flip it. I don't want it to be intimidating. We do have to deal with calculus now, especially in physics 204. We have to sort of deal with it in the real way. That is, knowing when to set it up, why to use it, what it means, and then setting it up ourselves. So the flip is that, honestly, in my heart of hearts, I didn't understand the calculus. I could do it, but I didn't get it. And I knew I didn't get it. And I was afraid of it until I was sort of like forced to see it in a physics context. And once I saw it in a physics context, what for me was true is I would have rather had physics as a prerequisite for calculus rather than the other way around. That's what I thought. So I don't know if that applies to all of you in the class or not, but what I'm taking too long to say is, in the other section this morning, I spent 75 minutes actually, and you'll see on these pages, and I'll give you the notes, you'll have the notes, really trying to explain in physics terms, in general terms, not in like nitty-gritty terms, but trying to explain really what an integral is, why we were setting it up here, why it applies here, what a continuous sum is, blah, 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 and what the fundamental theorem calculus is. Now, hold on. We will use a lot of calculus in this class, like on, oh, yeah. I mean, it's mostly integration in this class, but there's a lot of it. Okay, so I'm telling you all, I mean, I'm answering John's question. I'm telling you all that now that we're in physics 204, I'm not saying the integrals are super hard. They're not. Like, most of the integrals are actually straightforward once they're set up and once they're there. They're a lot easier than a lot of the, I shouldn't say easy, but they're a lot more straightforward than a lot of the ones you've done in math class. But the tricky thing in physics is you actually have to know when and why and how to use them. You have to set them up. And like a lot of people often say when they get to any physics class, but especially 204, people, and you've probably heard me say this before, many of you, a lot of people will say in physics a lot of time, like, yeah, I get it. And I get what he's doing, he, the professor, what he or she is doing when she does it in class. Like, I get it, I can follow it, and I can even like do the physics once you start me up, but I never quite know how to start it off or what the question means, or I never quite know I don't know how to choose which equation to use. Once it's going, I can do it, but I don't know how to start. That's almost my 13th. I was almost my 13th reason to what? 13th reason. I think that's an expression I don't know. But for a lot of people, they'll say they get physics, except they just don't ever know how to start it on their own. I'm totally sympathetic to that. And that was me too. That still is me, except that we also have to realize now that we're in physics 204, that is what physics is about, is knowing how to start physics. Like, the doing it once it's already set up and started, that's actually more the math, to be honest, or it's more the computation or something. So on the one hand, the rubber's going to hit the road here. We're going to have to actually get what integrals are and get how to set them up and stuff like that, and when and why. On the other hand, therefore, I'm taking, as usual, way too long to say this, but therefore, I try to do, like, I'm not assuming you're comfortable with calculus. I'm assuming we need to get comfortable with calculus. And I'm assuming that if you're anything like me, this might be the opportunity. It's not too late at all. This might be, and for many people it is, physics might be the opportunity to actually, for once, actually start getting what the calculus is all about and why and when. So that's what I did all this morning. Okay. And it's in these notes, and you're going to have these notes, but I highly recommend, please, that you watch the video like later. Watch the video once it's posted. Watch the video from the other section from this morning. Like technically you're called afternoon and they're called noon for when I post the videos in the 204 playlist. Okay. I not only recommend, I urge you to watch the video from this morning, because especially if you have any anxiety or anything or discomfort or curiosity about the calculus, particularly of integrals and like what they're about and stuff. Okay. Like the fundamentals of integrals. I did that this morning. I'm not going to do it again now. I'm just going to waste all your time talking about it. I highly encourage you to watch the video. I'm going to go to something else now. And I told them to watch your video about this. Okay. We're going to be efficient that way. I'm going to go to something that's more physics directed in a moment. I'm going to go show you what, assuming you can get this integral, I'm going to show you what we do with the result of the work integral, what it's for in physics. That's what I'm going to go to now. And I'm also going to say, since I'm spending all this time telling you to watch the other class video, and of course, technically I can't require that. Well, I guess I could as homework. Yeah, maybe that's homework, okay? Because you're not gonna have another sheet for a while. Please watch the video from the other section. And conversely, or as compensation for that, we're actually gonna leave class early today, okay? I'm spending all this time telling you, I'm gonna teach something now, but we're gonna shut down earlier than usual. We're supposed to go to 4:30. We're not gonna go to quite 4 today, for good or for bad. I apologize, or you can thank me. But okay, so I'm saying these notes right here that I'm just like flying through, this is like the buildup of the work integral. Work, one thing I want you, work is the integral of force with respect to displacement. Work is the integral of F dx. In simple cases, that means it's force times displacement. What do I mean by simple case? I mean a case where there is a force that you can multiply by displacement. When the displacement is small enough that there is a recognizable, identifiable, constant force, multiply the force times displacement, that's work. Work is the ultimate consequence or outcome or accumulated effect of pushing or pulling something through space. That's what work is, okay? It's force times displacement, but it's an integral. It's the continuous sum of a bunch of little forces times displacements in any case where, in a general case, where the displacement is large enough to allow for varying forces. If the force is not just one number, if it's getting stronger and stronger and stronger, or weaker and weaker and weaker throughout some displacement, in order to account for it, so that we can't just say multiply just one number of newtons times one amount of displacement. If we want to add up all the force times displacement times force plus force times displacement plus force times displacement plus force times displacement for a large displacement over which the force is continuously changing, then the process for doing that, for adding up a whole bunch of little products, of little force displacement products, the process for adding up a continuous sum, as in an infinitely divisible sum of force displacement products, is an integral. An integral is a continuous sum of product. That's what I talk about, like in the video. That's what these notes are about. Okay, blah blah blah. Again, I will obviously put these notes. Well, yeah, I will put these notes. No, sorry, in Google Classroom. But then, and I want you to watch that video, please, please, please. But now what I'm going to do for about a half hour, an hour, 40 minutes, is I'm going to say, I'm going to go to the next step or the next question, which is, okay, once we do that integral, once we get the force, once we get the work in any context, specifically this context of a spring, once we get the work, what's the point of that? Like, what do we do with it in physics? Totally fair question. That's what I want to address now. So. Yeah, so this is all, sorry, good question, John. All that we're talking about right now is in the context of question 4 on the sheet. I might have told you the answer, maybe even more than one time, but as far as I'm concerned, we still haven't actually, I remember now in this class, I even like jotted down a solution for you to copy, but I don't think I've explained it to my satisfaction. So I'm still breaking down, unpacking, and explaining how to get an answer to question 4. That's right. Thank you for asking. And question 4 is, so really in broader terms, what we're really asking here, what we're really talking about here is how, if you're given a spot, how do you get a speed? How do you get velocity as a function of position rather than as a function of time? When you want to know velocity as a function of time, you do kinematics, you do A equals V minus V naught over T, you do the constant acceleration equations, you do F net equals ma, like we were doing really in questions 1 through 3. But if you want to know how velocity or speed is related to position, particularly when force and therefore acceleration are not constant, then you need to do work and energy. And that's what I'm talking about here. I mean, so John's absolutely right. I'm talking about question 4. And I'm just trying to be as clear as possible. But again, by the way, again, we're leaving early today. You are welcome to remind me at 10:04, any one of you in the chat, politely, please, can just remind me, please, like we got to shut down, and we will. And again, I apologize, but the rest of the material, watch the other class video. What? Say, please remind me at 10 minutes to 4, please. And then we'll leave like about 5 minutes to 4, we'll leave. Okay, thank you. So this is all in the context of F is not constant, A is not constant, but we want to know. Whoa, what just happened? I don't know what just happened. Sorry, hold on. Okay, sure. I know someone's trying again. Okay, so the question I want to answer for you now, in in approximately 40 minutes, or whatever, is in physics now. So this is a physics thing. I'm introducing work because I have a force that's varying continuously as a function of position. But so even assuming that I could solve it, so I say that work is the integral of force with respect to displacement. But even if I could get that integral or compute that integral, which the previous pages tell us how to do, and the other video will tell us how to do. So what? What do I do with that integral once I get it? What's the point in physics? And again, let me say, I mean this in general, I'm trying to answer this question, but yes, particularly for the purpose of question 4. So here's the answer. All right. So if I examine any small interval of displacement, small enough that the force is essentially not changing, if I examine any little bit of work, work is force times displacement. If I'm looking at the total amount of work being done through displacement, the total amount of force, always by Newton's second law, equals ma, right? So force through some displacement equals ma through some small displacement, right? But if we're talking about a small interval where force is essentially constant, where there's one force act, where the net force is essentially constant, then the acceleration is essentially constant for that small interval. And that means for that small interval, we can use one of our constant acceleration equations, such as this one, whether you've memorized it or not, whether you look on your equation sheet or not. One of our old equations from physics 203 is a equals v squared minus v naught squared over 2x. So, excuse me, so I can substitute that in to the a there, right? And say, and tell me if you want me to go. So for a small amount of work, and the delta x is canceled. What we're saying then, over every little bit of work you do, the net work you do, like the net force times the displacement, the net work you do over every little displacement seems to be 1/2 mv squared minus 1/2 mv naught squared. Right? I'm going to write that again on the next page. Right? Like that's just algebra. And that at this moment in doing this algebra, I'm not saying that at this moment, I've never heard in my mind, I've never heard of 1/2 mv squared or anything. I'm just saying algebraically, it seems that if I push or pull something through a small displacement, then the number of joules of work I do on the left-hand side seems to be, according to the right-hand side, yes. Yeah. Well, it seems to be, well, exactly what Stephanie's saying. So she's saying it publicly. Hold on a second. Yeah, no. You're like totally correct. Still, Stephanie is, She's saying v is like any velocity, right? It's an instantaneous, and really in this case, almost like a speed, since it's being squared. And so if it's being squared, we don't even care about minus signs and plus signs. So yes, v is any instantaneous velocity, or really the magnitude of any instantaneous velocity. So v is any speed at any moment that we're looking at. And v naught would be the original, the initial speed at the beginning of whatever interval we're looking at. Stephanie is totally correct. So that's a really good observation. So therefore, I'm just going to write the same thing on the next page. Like, remember, like x minus x naught means the difference between position now versus initial position earlier, right? Like, that's just an example. Like x minus x naught means the difference between two positions, one now and one earlier. So x minus x naught means how much we've changed our position from then to now. X minus x naught, just an example, is displacement, right? Or similarly, like you might remember, a equals v minus v naught over t. Average a bar equals v minus v naught over t. What average acceleration is defined to be v minus v naught over t, the difference between some instantaneous velocity now versus what it was earlier at some initial velocity v naught, all over t, like the difference in velocity per time. What I'm saying is, or I'm just reminding you, like, if you ever in physics see variable minus variable naught, then it means exactly what Stephanie put in the chat. It means like the difference in the value of that variable from some earlier initial point when we were paying attention to now. Like the blah minus blah naught means the change in the value of blah from earlier to now. So now what this algebra is saying, now this algebra is saying something that looks a little bit more complicated. It's saying, apparently, if you do work on a system, if you push a block with 3 newtons of force through a 5-meter displacement, right? You've done 15 joules of work on that block. Like that's what the left-hand side says. What the right-hand side, just from algebra, seems to be implying is, okay, if you did 15 joules of work on that block, of what you thought you were like pushing it or pulling it through a certain displacement, right? You were interacting and bringing about some change in that block's position. Well, the right-hand side says, oh, here's something interesting. The right-hand side says, well, you know what, weirdly, like you never think to care about this before, but like before you started that experiment, if you were to take the initial speed of that block when you first started pushing, and which might be 0, but no one's saying it has to be 0. Like when you started pushing that block, it had some speed. Maybe it was 0, maybe it wasn't. If you take that speed and you square it, just bear with me for a minute. If you take that speed and you square it, and then you multiply it by the block's mass, and then you divide that whole product by 2, and you say, why am I doing that? What? I have to square the speed, multiply by the mass, divide by 2. And I say, yes, just do that for a second. Just take those numbers. Just measure the speed, square it, measure the mass, multiply the 2 together, divide the whole thing by 2. Now, write that number down. right? Write that number down somewhere. The product, like call it whatever you want. Call it the half mass square speed. Put that in a bag. And then you might even say to yourself, oh, okay, it's a measurement, it's a bunch of measurements. I'm multiplying them together. I'm like getting this weird combination of measurements. I'm putting it in a bag. Are there units for this measurement, you might say? And I would say, well, yes, as a matter of fact, for this mass times a half times square of speed, the units are kilograms times meter per second. Wait, hold on. Sorry. Oh, funny. I think I get that. I think that's funny. I think I get that. I think that's funny. I'm not sure. But yeah, so you put all these quantities together, you write them down, and you might say, what's the deal with the units? Well, the units would be kilograms times meters per second squared, quantity squared. So in other words, kilograms times meters squared over second squared, which is to say kilograms times meter per second squared times meters, right? Just think about that for a second. Just think about so the units are kilograms times meter per second squared times meters. Now you write that number down, somewhere, and then do your work. Do your 15 joules of work on this block. Now, when you're done, measure again. The square of the speed, measure the speed, square it, multiply by the mass, divide by 2, write that new number down. It's going to be a new number. It's going to be in the same units, but it's going to be a new number. Now back up and look at what just happened, and you'll notice something is what we're saying here. And we're saying this is a double equal sign. This is a discovery, like from algebra, but this is discovery. It's not a definition. We're saying, now look, say you did 15 joules of work on that block. Remember, a joule is a Newton times a meter, right? It's like a unit of force times a unit of displacement. A joule is a Newton times a meter. A Newton is a unit of force, like F equals ma. A Newton is a kilogram times meter per second squared. A Newton times a meter is a kilogram times a meter per second squared times a meter. You did 15 joules of work on that block. Now look at your two numbers. If you look at what is 1/2 mv squared was originally, and you compare it to what it is now, that is, you subtract them, subtract what it was originally from what it is now, you're going to get a number that is also measured in kilograms times meter per second squared times meters, right? Like they're both in this, both sides of this equation are in the same units, I'm saying. And what you're going to find, as this equation says, is if you compare your 1/2 mv squared at the beginning to your 1/2 mv squared at the end, the difference is going to be exactly 15 joules. That's what this thing is saying. And you might say, wait, that doesn't make any, like, why would that be? Just because of algebra is what it's saying. And here's the thing, put it the other way. Like, the algebra says that the speed doesn't, it says that when you do work on something, if you do 15 joules of work on something, you don't give it 15 units of speed. No, that would be nice, really nice and simple, but life is not that simple. And plus speed's not even measured in joules. It's saying when you do work on something, you give it something. What you give it, or what you take away from it, what you change in the system is this complicated combination of quantities. The quantity to track when you're doing work on something apparently is this weird combination of v squared times 1/2 m. Now, it's not that weird because it's actually it's one of the simpler combination of quantities that would give us the right units. But what this is saying is that from here on in, if you ever want to see what effect you have on a system when you do work on it, when you push it or pull it through a displacement, don't just track its speed, don't just track its mass, track the product of its speed squared times half the mass. Right. So on John's point, I want to be very careful on this. John's totally right, but I want to be very careful about this now. It's a great question when he's asking. What I'm saying now is, on the next page, I definitely agree with him, but I just want to be careful about it. I'm saying net work equals change in this weird combination of quantities, 1/2 times mv squared. Therefore, we make a decision as of this moment, like as of this moment in history or in the class, whatever, we make a decision from here on in to start tracking this combination of quantities from here on in, we're gonna track the 1/2 mass square speed of a system. Like what I'm saying is, of course, John is right. And of course, I agree with John. I do agree with John, but I want to make it clear. It's not like going at this period in history or in this period in the proof. I don't have any, I've never heard of, I never noticed this 1/2 mv squared thing before. Now I'm noticing it's worth paying attention to. So I'm going to give it a name so I can pay attention to it from now on, because it seems to be the number of joules that seems to get altered one way or another when I do work on things. In fact, if I do positive work on something, if I push something and it goes in that direction, I seem to add 1/2 mv squared to that thing. If I push something, but while it's going the other way, if I push against it, I seem to take away 1/2 mv squared from it. So I'm going to give it a name. I could call it the 1/2 mass square speed, but in fact, what I end up calling it is exactly what John says. We will name it kinetic energy. And of course, you spent your whole life here, well, your whole scientific life hearing of kinetic energy. I just want to make clear to you now, again, I'm not saying here that work ends up equaling this other thing that you know about from some other context called kinetic energy. I'm saying this is where kinetic energy, in effect, gets invented or discovered or whatever. This is the first time we introduce it as an idea. It is just the quantity that, according to algebra, it's the package of measurements that seems to be altered by work, by network. So from here on in, we say I'm just looking in the chat. Wait. Okay, just be careful. So I'm talking about kinetic energy. We will definitely get to potential energy. Just hold your horses for a second, if you don't mind. If you're in a barn. I just want to clarify now something that like sort of eluded me for a while. Just like what force is an interaction between two objects. What force is a push or a pull. What force does is it contributes to acceleration of objects, right? That's an analogy. Similarly here, what work is, triple equal sign, what work is the continuous sum of force through a displacement. It's the integral of force with respect to displacement. That's what work is. Why we care about it, what it does is it changes the 1/2 mv squared, what we're now going to call the kinetic energy of a system. Like that's what it does. Let me be more specific too. We'll get to potential energy shortly, i.e. Wednesday. And again, I know for many of you, this is old news and fine. Hopefully it's clear. I'm just trying to but for some of you, it's new news, number one. Number two, I'm just trying to give you the perspective on this that I think works in this class or for this physics material. So work is the integral of force with respect to displacement. What work does, what a consequence of it is the change in what we're from now on calling kinetic energy. To put this together in English now, what I'm saying, kinetic energy is 1/2 mv squared. But what is the meaning of that in English? From here on in, kinetic energy, the package of measurements put together in this funny way, the product of 1/2 of your mass times the square of your speed, that number of joules, that number of joules that kinetic energy is something one system has. Work is something one system does to another. Kinetic energy is like a property, or what you might call a state function. It's like a state of being, a description of a system. Work is something one system does to another. Kinetic energy is a commodity. Work is a transaction. It is, in fact, just like money in economics in this respect. The more kinetic energy I have, the more force times displacement I can do to some other system. The more kinetic energy I have, the more work I can do on another system. Like, that's its purpose. When I do work on another system, I give up some of my kinetic energy to that other system. And that other system gains precisely that amount of kinetic energy. Work, in short, the fine way to put this whole thing, and again, I know in a way you know all these pieces already, but to me it helps to have them in this perspective. The sum total of this whole thing is okay, I'm going to read that chat thing in 1 second. I'm just going to say, just like with money, why do I want a lot of money? Because the more money I have, the more I can spend, which means get rid of it, right? The more money I have, the more I can give to a storekeeper, a shop owner, or whatever, or an Amazon company. And when I do a transaction, when I give money to Amazon, I have that much less, and Amazon has that much more. It's like conserved in that sense, right? The act of giving the money over is the transaction. The amount that I have is my wealth. Same thing here. Kinetic energy is the ability to give up kinetic energy in a transaction or transfer that we call work. Work is the transfer of energy from one system to another. If my system does positive work on you, that means I send energy to you. You gain, I lose. Precisely that number of joules. If I do negative work on you, that means I gained, you lost. Precisely that number of joules. Work is the transfer of energy. If no work is done at all on a system, then the total amount of energy does not change at all. All of this is things you've heard a million times. I'm just trying to spell it. So mathematically, work equals 1 of mv squared minus 1 of mv squared naught. And I am watching the clock, but now I just want to, so I do want to put that. So the reason that I care about that integral, like work, is because it's going to ultimately let me solve for V, which is ultimately what we're trying to solve for here. Like, ultimately, this transfer of energy thing is the bridge between V and X, between speed and position, which is exactly the relationship that we're looking for here in question 4. So we actually almost are over. And I'm going to look in the chat now, and I'm guessing that maybe one of the things in the chat is the reminder that we should end soon, which I appreciate. Let's see, chat. Capitalism is funny. Okay, state. Okay, John, that is funny. State function where amount of mass you have more problems. Wait, so sometimes I can't tell the jokes and serious, and the jokes are funny, but I think John Ford's question is a serious one. When I say state function, I mean a description of something at a certain state, in a certain state. So, like, 1 of mv squared is a state function just in this. I'm not saying, I'm not trying to say something super deep. I'm just saying, like, right now at this moment, yeah, like if I know the amount of mass, that's something else, and I know its speed right at this moment, then I multiply the two, I square the speed, I multiply by the mass, I divide by 2, and I have this description called kinetic energy. It describes the system right now. A little bit later, the system might change because work might get done on it. So I might have a different amount of kinetic energy. So a state function, something that describes a system at a point, as opposed to work. Like work is not a state function. It's not a description of a system. It's something a system does to something else. Again, this is my economic analogy, and obviously it's a loose and kind of ludicrous analogy, but kinetic energy is like the amount of money you have, and work is the transaction itself. Okay, one's more like an adjective and one's more like a verb. Yeah, this does. No. Okay, and that is a serious. John Gord's question is totally reasonable and serious. Ultimately, the physics definition, this chemistry definition, do ultimately coincide. I'm not, and I know what you're talking about, and that's great that you're carrying it over. I'm meaning it a little bit looser right now. I'm not denying those chemistry details. I'm just not using them at the moment. But yeah, okay. Sorry for this. Now, okay, yes. Oh, great, Elizabeth's question, and we are going to wrap up in a couple minutes, like I warned us. But these are great questions. Elizabeth's question in the chat: the spring does work on the mass, which is changing the KE of mass. Yes, so exactly what Elizabeth. Sorry, I should read out loud. The spring does work on the mass, which is changing the KE of the mass. That is the point here. So yes, and that we're going to wrap. I'm going to do that, and that's what we're going to wrap today. I'm saying here, and yes, so let's finally get an answer here. Okay, I'm writing this part quickly, partly because we're going to go in 2 minutes, but also this part that I'm writing quickly is developed again this morning and on the video that you can watch, or for some of you it might be obvious anyway, but I'm saying if work, I'm saying work is a change in kinetic energy. The point of work is that it changes the 1F squared. So if you do work on if the spring does work on the mass, then the spring is going to change the 1F squared of the mass, like as Elizabeth says. So what is the work that the spring does? Well, it's the integral of the force exerted by the spring with respect to displacement. The force of the spring is negative kx, Hooke's law spring. So I'm literally going to integrate negative kx. But the spring is bringing the mass in. My apologies. The spring is bringing the mass in from some initial position that we called x naught, right, to the equilibrium position. My bad. Right, we're looking at the mass as it comes, and again, I talk about this in the other lecture if you care, but as the spring is coming in from that original 15 centimeter position x naught to the place that we're solving for, the equilibrium position x naught, as it's coming in, we want to know the work that the spring is doing on the way in. The force exerted by the spring is negative kx. So we integrate negative kx from x naught to 0, right? And now I'm going to the next page. So work done by the spring is the integral from x naught to 0 of negative negative kx dx. Now, I can multiply that by -1 to get rid of the negative sign, and thereby I flip the limits of integration, right? I mean, I hope, again, I sort of talk about that in the other thing, but you also sort of know that from math class. Like, I can get rid of the negative sign by flipping the limits of integration, right? So then that becomes right? So the work done by the spring, and this is the last page, definitely in the last couple of lines, I'm going to write. The work done by the spring on the mass is 1 to bring it in from x naught to 0. Technically, it's 1 fkx squared minus 0, you could say, but it's 1 fkx squared is the work done by the spring. We're saying that changes the kinetic energy of the mass, right? So on the next page, on the final page, you don't really have to write the minus 0, but I'm just sure. As the mass comes in, but what is the initial speed? In this case, the initial speed of the mass at x naught at 15 centimeters is in fact 0, right? So we say 1 fk x naught. And this is, I know I wrote this originally for you like a week ago or something, but this just expands it out. So, and we're solving for v, and try to always save the numbers for the very last minute. So we say v squared equals k x naught squared over m. So v equals square root of k x naught over m. So v equals 200 times 0.15 squared all over 0.3. And that equals, I always forget if it's 3.87 or 3.78, but I think it's 3.87. Someone correct me in the chat. I think it's 3.87, but if it's 3.78, could someone tell me in the chat? It is 3.7. Which one? Sorry, 87 or 78. I'm sorry. Sorry, which one? And we're 87. Okay, great. Thank you. Okay, so that's the answer. So what and we're going to end right now. But what I'm just, and again, for some of you, this is like old news and boring. I apologize. For others of you, maybe not. But what I'm holding the whole class responsible for now, what I believe we know in this class, whether we've seen it before or not, is we now know work is the integral of force with respect to displacement in general. Work is integral of f dx. Work done by a spring, therefore, is 1 fkx squared. Like that's a thing now. And what work always does in all cases is it changes the 1/2 mv squared of a system. So work is difference in 1/2 mv squared. In the case of a spring, the difference in 1/2 kx squared equals the difference in 1/2 mv squared. So for this particular problem, even though I know I gave the answer last week, the answer is 3.87. Please watch the other video, but that's it for today. Thank you for being so patient. I do have to run today, but I'll see you Wednesday, normal time for the full time. And then you'll see Professor Walters on Friday. Oh, sorry. Absolutely. Yes. So this is the last slide. So yes, have a good night. And everybody, I'll hold it for a second if there's questions, right? But yeah, bye guys. Thank you very much for your everything in the world. Thank you. Thank you. Thank you.